Good. Okay. I'm going to share my screen and welcome everybody to our intro to cloud computing, where we're going to talk about all sorts of things involving the cloud. But first, a little bit about my background and experience. So my name is Naomi. I'm a technical education specialist and a data science fellow at the eScience Institute here at UW. And in practice, what that means is I like to liken my job to being like a computationally focused Miss Frizzle. I like talking to people about problems they have and seeing if technology can solve those problems and working with them from where they're at to figure out how to use that technology. I really like thinking about technical problems. I really like thinking about pedagogy. So that's sort of what brings me to this space. In general, I like to abstract the type of work that I do into the description that I facilitate information flow between complex domains. And so that could be anywhere from using a compiler to compile programming languages to machine code, or using a lecture to teach people a complex piece of technology. If these are things that excite you too, I'm happy to talk about them offline. But for today, the thing that we are going to be talking about is cloud computing. Specifically, we're going to talk about the abstractions that underlie most of the cloud computing that you can do if you have a credit card or some good credits that are donated by a large corporation or an institute. We're going to go through a tour of some of the workflows, sort of how you actually use these resources in your day-to-day work. And then we're going to talk about meta skills that are going to be useful for your path when you begin using this stuff and you're not in the middle of a lecture setting. You're just sitting down at your desk and saying, okay, that all sounded good on paper. How do I actually put this into practice? After we talk about all that stuff, I'm going to go on a very, very brief demo where I will show you what it's like setting up a Jupyter Hub. So sort of the behind the scenes of what it's like to build the sort of coding interface y'all have been logging into all week. And then after that, Ariel is going to show us how to grab data sets that are stored on the cloud and use them in our work on our Jupyter Hub. But before we get into all of that, I'm sort of interested in what you all think the term cloud computing actually means. And so this is a prompt for you, but I don't want to hear your responses one at a time. I want you to think about this for like a minute. And then I want you to send your response to this prompt. What does cloud computing mean? To the Slack channel #Alterman-cloud. And so I'm gonna count you down in like a minute, but I just want you to type out what you think. Wait to hit enter until I say go. This is gonna be my waterfall of responses. This is my favorite part. Everything else is boring. It's gonna be horrible. Oh, thank you for the Magic School Bus reference. I see several people are typing. This makes me very happy. All right, ready? Hit enter in 3, 2, 1, go. Yes, high-powered computing. Someone else's computers. Ariel, I have a sticker that actually says that on my personal laptop. Don't ever let Rob see it. My boss is the director of cloud computing at UW. He would agree with it. Cloud computing means running code on a faraway computer I access over the internet. Remote computing, non-local computing, external computational resources. I really like the term resources here because it gets at a lot of different types of things. I guess it refers to computing not on site. I like the tone here. I don't always know what cloud means, and sometimes it can mean different things. Oh, cloud means hours of prep to get in. This is unavoidably true, but we're going to talk about that today. Using resources and computation that are non-local. The ability to have immediate, direct access to data storage and remote management. Yes, oh, spectacular. It is all of those things and more. The truth is, cloud is a sort of general term that people started using to refer to a bunch of different services that give you immediate access to resources. But what actually those resources are can depend on the company and the use case involved. So I want to spend a little bit of time just establishing the context of what cloud computing means for this session. When we talk about cloud, oftentimes, especially if you talk to someone from a non-computational background, what the term cloud means is that they have some data that they were keeping on their laptop, and they started having space trouble. So they put that data on an external hard drive. And then they ran out of space on that hard drive. So they got more hard drives. And eventually, one of those hard drives crashed. And so they subscribed to, or they used their institution's subscription to a consumer cloud service like Dropbox or Google Drive, which lets them upload files to someone's file servers, and it gets kept safe there. And if you think about sort of any service that you use on the web that you pay money for that manages things for you, you could talk about this as a cloud service. The way that we are talking about cloud in this session, however, and in general, when you talk to scientists about cloud things, scientists that are doing quantitative data analysis, that is, they're talking about something slightly different. They're talking about the technologies that underlie these consumer services. So if we lift the veil on top of Dropbox, we'll see that what's powering it is there is some computer that used to be running server software or computational software, and the computer was no longer powerful enough to do this job. Maybe it didn't have enough RAM or disk space, or the CPU wasn't powerful enough. Maybe your cat spilled a coffee on it. Things have been known to happen. And so ultimately what you do is you put your computers in a room with really good air conditioning and power backups, and you hire people to take care of this room, to make sure people don't break into it, to make sure if the building catches on fire, that they sacrifice their lives to get the hard drives out, because what are we if not supporting our institution? And ultimately, what Google and Amazon and Microsoft realized is that they can rent this out as a service to people. They can manage the rooms that have all the servers in them. And they could say, hey, you don't have to worry about if the building catches on fire. It's like the data center equivalent of the cat spilling coffee on your laptop. Sorry. I flail around a lot. This is a warning. So when we talk about cloud in terms of computing, we're talking about usually these three specific vendors' services. We're talking about Google's cloud platform, Amazon's Amazon Web Services, and Microsoft's Azure. And these are all in practice more or less the same thing. There are other companies that do all of these things too, or portions of these things. IBM does these things. Oracle does these things. There are a lot of startups that do parts of what all of these platforms do. But in practice, if you've learned one of these, then you can relatively doably learn the others. It's sort of like learning one programming language and then trying to move that knowledge to another one, like going between Java and C++. It's not easy, but it's definitely doable. And learning the skills for one definitely helps your mental model of how the other works. And so what we're going to be talking about for the rest of today is the mental model for how these services work. Because I think when we talk about an office suite like Google Drive, we are sort of trained to know that office suites mean having Word documents and having spreadsheets, maybe having a slide deck that lets you communicate information in a visual format. But the question is, and there's no actual answer to this question, this is a question that's still actively being thought about in industry and in academia. What are the equivalent of these abstractions for generalized computing? What can you easily give someone and say, hey, this is, your general purpose computing tool, but this is a more specialized computing tool that will be useful for you in this other way. You can imagine that maybe you can do most of what you can do in PowerPoint or Google Slides by using a word processor like Google Docs. But it's not going to be as effective. It might actually be painful. And so we're still trying to figure out what parts of cloud computing are painful and what parts are really effective at solving problems. And there are tons of people out there, some people in this room, that have developed technologies that actually help us to solve problems based on these like very fundamental primitives or like building blocks, like using a computer to run Python code. So the abstractions we figured out that have worked out pretty well so far are going to be potentially not earth-shattering from a computer structure point of view. They're usually split up into compute, which is to say a virtual machine that you can log into and do things with in the cloud, and storage, which is to say if you have stuff that doesn't fit on that virtual machine, what does your external hard drive look like, but in cloud terms? And so the terminology that you're going to see thrown around a lot when you're working on cloud computing is virtual machines, or VMs, to refer to the actual computers that are doing work. And then file stores or object storage for the places that you keep large amounts of data. And we'll get into the details of how all of these abstractions work. But effectively, the reason that we want to split these two is because the cloud is very interested in charging you money for only exactly what you use. And so for as long as this computer is turned on, it's charging you for the time that you're spending on it. And then you might want to turn this off, but still have access to your data, be able to download it, be able to share it. But you don't need a whole computer to do that. The data is just sitting on a hard drive somewhere. And so that's why we split it off into this other abstraction, this storage abstraction. And then aside from these two fundamental abstractions, these things that sort of build everything, unfortunately, we end up with other stuff. Because in order to manage all of these computers and all of these storage units, we need a whole lot of behind the scenes work to make it go smoothly. And so this is really the problem that a lot of non-IT people face with the cloud, myself included, is that using the cloud effectively asks you to start thinking about some of the things that IT people's whole jobs revolve around. So I'm going to throw up some other abstractions that you're going to see when you're using the cloud. It's not important to think about these and learn them deeply when you're first starting to use this stuff, but you're going to see these terms. And so I think it's useful to have them floating around in the back of your head. So we have networking, which is how you connect the hard drives to the machines. And you'll see the term virtual networks or VNets a whole lot. This is basically just referring to the idea of connecting cables between things or having everyone sign on to the same Wi-Fi network so that you can see people's files show up in your AirDrop, that kind of thing. We have users and security, that is, who can log in and see the computers you create, who has access to the files in your file store. The term that shows up all the time for this is IAM, which stands for Identity Access Management. This is usually the most bureaucratically complicated and annoying part of cloud computing because it's always there. It's critically important because you don't want to let anyone access your infrastructure. You want to make sure only people in your lab can. But it's also really tricky to get right and usually not your first priority. So most of the time, cloud platforms are set up so you don't have to worry about this that much, but it's going to come up at some point. You're going to see the term IAM in like some cloud dashboard somewhere, and you can know that it has to do with allowing certain people to see things and use things and other people to not have access. And then the last thing that I think is really worth mentioning, and this one I think is sort of cooler than the other two grayed out things here, but I grayed it out because it's not our first order priority, is this notion of blank as a service, AAS. And so this is what I'm getting to when I was saying we haven't answered what useful cloud abstractions there are to do work yet. So we know that we can give people virtual computers that they can log into and crunch numbers using Python on. But the question is, can we save people time and effort by not requiring them to do that? Can we say, just give you a Jupyter interface? Can we let you upload and download files just like Dropbox, but give you the flexibility of working with all this other stuff too? And so all of these things are referred to as Jupyter as a service or a database as a service. And what this means is effectively, it's still built on top of virtual machines and object storage, but you don't have to set that stuff up yourself. You can just log on to AWS's console and say, here's my Jupyter notebook, let me run this code and look at its outputs. And so this can be super, super useful to like getting started quickly and getting results without worrying about all of the infrastructural IT details. So whenever you see AAS, this is a key that there is some product that is taking work you used to have to do to configure things and keeping you from having to worry about it. The Jupyter Hub that we've been using throughout the week is an example of code as a service or platform as a service. I don't know what AAS, what do you say Jupyter is?
Notebooks as a service.
Notebooks as a service, yes. And actually, I mean, most cloud platforms have notebooks as a service. We aren't going to look at them today, but they all have their own brand name. They're not too hard to find if you Google for like cloud notebook upload and then your favorite cloud platform. And I'm happy to talk about all of this stuff offline, or if you have questions and want to ping me either through Slack, which I'll hear, or raising your hand. We could talk more about any of these things. So we're going to dive into a little bit of detail about how we think about and manage compute and storage, how we manage VMs and object stores. But now might be a good time to take a break and see if anyone has any thoughts or questions that they want to give me. They want to say something, which would make me happy. Yes.
Of the three cloud services, is there a preferred one for first, like an intro person to get into?
Yeah, that is a spectacular question. So of all the three cloud services, is there a good one for beginners to get started with? This lecture is being recorded, so, and I work with all the cloud vendors deeply in my job, so I don't want to anger them. I will say, I have a whole slide about this that all these things will be repeated for posterity. So, but to throw it out now, I think that the best thing for a beginner to do is to look at the people around them and what those people know how to use and using that. Or if you're using code or a data set that is inherently based on one platform or another, go where the expertise is. Because what you really, really want is someone who is willing to let you ask questions. I think that they all have rough edges and they all have very polished services. And so what might be really easy on one platform might be very hard on another platform. And so if you have the freedom to be able to try different platforms out, say if you do have the financial privilege to be able to put a credit card down and just say, I'm going to spend $10 on each cloud platform, you can try things out and see if you're digging how they work or not. And this is what I do when I do personal projects. I like check out the services. I like the term kicking the tires. I like kick the tires and try out the equivalent services on Microsoft's cloud and on Amazon's cloud. And I'm like, one of these is like hugely annoying. And the other one is like pretty okay. I'll go with the one that's pretty okay. And I wish I could say which ones are hugely annoying, but I will keep myself from it. I'm exercising such restraint. This is a good question though. Does anyone else have any questions? Okay. Well, let's start talking about computation then, which is ultimately what all of this is here for. So when we're talking about a virtual machine, of course, I'm a computer scientist by training, so I love introducing abstractions for my abstractions. So the way that we can think about a virtual machine is two aspects, body and soul. In the body of the virtual machine, the instance type, we have an instance of a virtual computer, and that instance has some amount of computation, some amount of memory. Maybe it has a graphics card that's really good at doing machine learning. And maybe it has storage attached to it because there's a hard drive in this guy. It's not big, but it has one because I need to save files, you know. Separate from all of that, there's an operating system installed on this computer. Maybe it's Windows, maybe it's Linux or Mac OS. Maybe if you really like pain, then you've installed BSD just for fun. I have friends in the BSD community, don't worry about it. Sorry, Ariel. So when you create a virtual machine, it comes with a stock image. And so when we use the term image, what we're referring to is everything that's on the hard disk. Now that changes over time once you turn the thing on and start installing your own files. But at any time, you can turn the virtual machine up and you still have the image. And you can duplicate that image and create multiple virtual machines that look the same as the one you just modified. You can also turn the virtual machine off and change the instance type underneath the image and turn it back on and have everything just more or less magically work. And so we can start to see why people really like this model of having things be virtualized. It's because if we use these as the fundamental building block for all of our work, then we can really easily resize a machine or create multiple machines if we want to do the same problem on different pieces of the data set in massive scale. If we have the funding for it, we could create 100 virtual machines that are all running our software and do the number crunching on a whole data set in a much smaller amount of time. And so to that point, my boss has a phrase that he likes repeating about these computers, which is we're used to naming our computers and treating them like pets because they are very expensive and we want them to hang on to like dear life for enough years that we amortize the costs of the machine and not have to pay for a new one every year. That's not the case in the cloud. In the cloud, these things are charged per hour of on time. So in general, you want to turn a machine on while you're using it and then turn it off as soon as you're not using it. Like, I would certainly want to turn a virtual machine off when I go home at the end of the day. I might even want to turn a virtual machine off when I step out for lunch, because these things don't cost that much per hour, but that really adds up if you're running it 24/7. And so because of this, we like to say cattle, not pets. We don't give virtual machines names. We don't expect them to live long and fruitful lives. As much as it pains me to say this as a vegetarian, they are not fed grass-fed diets. We kill them very quickly. We create them and we destroy them because these are units of computation. They're fungible resources. They're not things that we customize and keep around for a while. And this is reflected in some of those as a services that I was talking about. There are now clusters as a service that allow you to think about computation as submitting a job to a big batch of virtual machines that you can scale to be much larger or smaller as you need it. So normally, when you're just playing around with data and beginning to think about how you're going to explore it, you have one virtual machine. When you're trying to see if some of your hypotheses hold water, you might scale this up to work on a larger data set, and now you'll have 5 or 6 VMs. And now maybe the publishing deadline is coming up for your paper. You're going to scale this up to be 100 VMs so that you can really get the results you need. And then as soon as that's done, you shrink that cluster back down to be 1 or 2 virtual machines again. And this is why people like taking on the risk of charging for compute time per hour rather than just buying a computer and using it. Is because suddenly you can always tune this to be exactly the type of machine you need and in the quantity that you need it. And so if you just like do the math about how much this computing costs, it's not always immediately obvious how doing things with virtual machines in the cloud can be cost effective compared to doing it on your local cluster at your institution, if your institution has one. The way that this becomes really effective is when you start thinking about these resources in terms of flexible plastic things that you can shape to meet your needs and you can optimize your costs for. And that's an art and a skill. I'm not that good at it. My boss is super good at it. I suspect Ariel is very good at it. These are things that are like very good to begin playing with so that should you ever be in the position where you can use these sorts of things, you have a sense of how you're going to create a cluster, make it big when you need it, make it small once you're done. And in terms of making it big or small, Unfortunately, for most of these platforms, it's not as simple as just saying how powerful of a CPU you want. There are these notions of different types of virtual machine, and they all have their different names. So on EC2, on Amazon, there are T2 instances, M5 instances, C5 instances. There are series of virtual machines that are all built around one specific type of processing. And this is sort of a deluge of names, specifically to let you know that, like, I am very bad at keeping track of what all of these mean and how good they are. When it comes time to actually create a virtual machine, in general, you'll be given a table that shows the cost of running one of these things per hour, and you'll be told how much RAM it has and how many different CPU threads it can support. So what you want to do is start with a small virtual machine when you're beginning to research things. When I say small, what I mean is like 2 vCPUs, which means it can be doing 2 things at once in its head, and 2 gigabytes of RAM. It's a pretty smaller amount of RAM. That's smaller than most laptops that you'll be able to buy on the market, but it doesn't have to do things that your laptop does, like run a screen 24/7. So you start with that. You start trying to do your work. And then at some point it'll freeze up and it'll literally just stop responding. You'll have to like go to the cloud panel and hit the stop button in order to get it to, actually reboot and respond to commands again. While it's stopped, you make the VM bigger and you try to redo your work. Maybe you make it much bigger, but you try to home in on the right size that lets you do your work without spending too much money and without having the virtual machine freeze up. So you can think of this as like buying a laptop. The laptop's not good enough. It freezes up all the time, so you have to buy a bigger laptop. It's just that this is really easy to do on the cloud because this is all virtual hardware. This is all easily changeable while the thing is turned off. So I think that the real skill ultimately becomes not remembering all of these different instance names so much as understanding the type of problem that you're trying to solve. Because this isn't a linear scale from not powerful to very powerful. This is triaged into a few different types of powerful machine. So there's general purpose, which is to say, this is a good computer. It's good at doing things. It likes numbers. And then you have compute optimized, which is to say, it doesn't have to remember that much at any one given time, but it's really, really, really good at crunching numbers. It loves doing nothing but multiplication. And so if you're trying to do things like, say, multiply large matrices together, this might be a really good type of computer to use because ultimately it's not going to be storing terabytes of data in its head. It's mostly going to be doing a lot of math. On the other hand, if you want to store terabytes of data at one time, say if you want to look at a cross section of a whole data set and say like take the average of some feature across gigabytes and gigabytes of samples, then you might go for a memory optimized computer. And this is because while it's okay at doing multiplication and doing computation, what it's really good at is remembering all of that data at once, rather than having to swap it into its working memory from like a filing cabinet on the other side of its room. And then you have other types of machines as well. You have storage optimized, which doesn't show up in this kind of work as much, but like if you need to be able to work with databases a lot, this is the kind of instance that might show up in a lot of web services like WhatsApp or Facebook use a lot of storage optimized computers. GPU instances are like compute optimized instances, but they have graphics cards attached to them, which are very good at doing machine learning. I can get into all sorts of detail about why that is. I think it's very interesting that GPUs ended up being good at both graphics and machine learning. But ultimately, what GPUs are good at is doing the same little problem bajillions of times in unrelated sectors of a data set. So whereas compute optimized is just focusing on one problem and doing it very fast, GPU optimized is doing the same small problem a whole lot all at once. And then separately, there are just the like beast computers that are insanely good at everything. And these are the ones that cost like hundreds of dollars per hour, and most people don't need these because you don't usually need to be good at all of these things at once. And so the whole point of my soapbox talk right now is that it's not so important that you know all of these different virtual machine series, so much as you're good at figuring out what type of problem you're tackling at any given moment. Is it compute heavy? Is it memory heavy? Can you benefit from doing things in parallel with GPUs? You don't have to worry about giving the wrong answer to this kind of thing. It'll be immediately clear if you guess wrong that the computer just won't work very well. It'll probably freeze up. And that's good. You can try the other thing. And you can learn to identify what types of bottlenecks you're going to be facing. These are the sorts of things that we think about in computer engineering all the time. And we sort of just expect people to realize that's a trade-off, but I don't think it's called out as a specific thing to think about. And so if you take away anything from this part of the talk, I hope you think about this kind of thing whenever you're facing a computational problem. Yeah.
Do these virtual machines provide public website hosting services?
Sorry, do they provide what?
Public website hosting services.
Oh, yeah, they do. So like public web hosting, like can you like serve a web page from one of these VMs?
And access it from the internet, is that possible?
Yeah, totally possible. And so like, I think that not only is it possible, but they were initially built to do good things or to do things like that well, especially general purpose computers. What they mean by general purpose is that they're actually optimized to serve websites like the way that you're suggesting. They also these days provide websites as a service. This is called serverless computing because the idea is instead of having a web server on a computer that's serving your website, instead your website just exists. You give it the HTML web pages, maybe you give it Python scripts that you want to run when people click the compute button, but ultimately you don't have any notion of a virtual machine that you're managing. Secretly, there is a server behind this website. It's just you're not thinking about it. You're not configuring it. And there are really interesting cost trade-offs with that kind of thing. It can oftentimes be much cheaper to do things that way, but it can take a lot more time, and because you have to learn how all these things work. And depending on your problem, it might actually end up costing more. These are all ways that they can cut corners about certain aspects of computing and do things more efficiently because you don't have visibility or control into how the server computer works. And most of the time, that's fine. Like if I have one large file and like if I have a static website, the kind of thing that can be hosted on GitHub pages. And I have a few large files that I want people to be able to download. This is the kind of thing that I can serve from the cloud without even having to create a virtual machine by using some of their website as a service platforms.
So, for the
Yeah.
three vendors you mentioned, Amazon, Google, and Azure.
Yeah.
All I heard is that they provide hourly rates.
Yeah.
Are there any yearly rates to buy virtual machine from one of the vendors?
Yeah, that's another great question. So like hourly rates versus yearly rates for some of these resources, these are called reserve pricing. And so normally the initial default assumption is that these things are all pay as you go. So they're hourly or they're by the minute. Some of them are even by the millisecond, depending on what type of service you're using. But you can get discounts by committing to saying, I'm going to pay up front for this usage for a year. That way they can provision these resources and put them in their spreadsheets of knowing what they need to pay for over an Amazon HQ. And it gives you some discount. And oftentimes like on the like pricing page for, let's actually like pull up the Ec2 Vm pricing. You'll see these tables of like how much a given instance costs. And next to so you see there's an on-demand hourly rate. I don't know how to find it here, but depending on the platform and the service, there will be another column here that says like 1 year reserve rate. And you get discounts for that. You also get discounts for all sorts of other commitments. Say if you know you're going to store a file for like longer than 3 months. If you have a static data set that you know is not going to change, then you can host it more cheaply than if you don't tell them anything about how long the data is going to last. Yeah.
If all you need is a GPU to do machine learning, there's also Google Colab, which is about $10 a month for like over $1,000 GPU that you have access to. That's
Yeah.
pretty convenient and more simple than all of it.
Oh, totally. Yeah, so Google Colab is exactly like a really nice way to get access to GPUs. And an interesting example of sort of this straddling between consumer cloud and infrastructural cloud, because ultimately what they're doing is the same thing. It's just they're really avoiding having us think about any of this stuff, which is something that I hope all services get to eventually. Because the fact that we have to have this session and learn about these things is very much an artifact of like right now. If you look at how computer graphics for video games worked, when people made video games in 1999, they had to understand a whole lot about how computer graphics worked in order to make relatively simple games. Nowadays, you have tools that let artists make spectacularly beautiful video games because they don't have to learn all of the details of how the hardware works. And I think that we're at a really interesting point in cloud computing right now, where it's beginning to get there, where people are beginning to provide things like Colab that let you reserve a GPU for a small amount of time, do the machine learning you need, and call it quits. And as these things get developed, I think lectures like this are going to change a lot, and that's really good. I, as an academic, like saying, as an academic and as a computer scientist / electrical engineer, I like saying the principles we learn in this session are useful broadly everywhere that you go, and they can change the way you look at the world, maybe for the better, but ultimately, yeah, hopefully we have less to worry about as time goes on. Yeah.
Yeah, I mean, first off, I'm wondering more about like what, so you're like looking at this, maybe like a lab or something, and being like, we need this amount of stuff to help like our computations, we're gonna purchase this, like, exactly whatever it is. How, I'm curious to hear more about like how that relates to the physical like hardware, like there's servers somewhere, like we're sharing this with how many people, and like also would like scaling up make any like sort of physical like difference in terms of hardware, and like is there some sort of energy or like environmental stuff that we should be thinking about?
Oh man, these are such great questions. Such great things to think about. Thank you for posing these concepts as even things to think about, because I feel actually sort of guilty now having this like silly like Jetsons cloud image of saying that we're living in the clouds, when in fact these things are using resources and like having a serious environmental impact. So at a technical level, what is going on is that there are these rooms full of server computers, and a given server computer has a CPU that has a bunch of cores inside of it. And a core is like sort of this is where I betray that I don't know anything about neurophysiology, but like, presumably there are different parts of my dad's a neuroscientist, I should know these things. Presumably there are parts of your brain that can operate relatively independently, like the visual cortex is operating independently of things in your neocortex and stuff like that. So you can think of a CPU core as being sort of like a generalized thing that can do math and do operating system things. And in a computer like this one, there are maybe 4 cores, which means it can think about things, 4 different things in parallel. These things have processors that aren't generally available in consumer computers. They're server line processors. Like Intel's Xeon series or AMD's series is called Threadripper, which I've always thought was a fun name as a SOist. And so those things have like hundreds of cores. And so then there's this question of, when we have a virtual machine, what actually is being taken up here? And so what's happening is an AMD Threadripper on one of these racks is being told it has some operating system on it, it's probably Linux, and it's going to say, hey, create a virtual machine in which you're running this software. And this has hundreds and hundreds of gigabytes of RAM. So it's probably fitting, I would say probably 4 or 5 virtual machines on it at any one time, depending on their size. And you're effectively being time shared the cores on this processor invisibly. This was a really big hardware advance that was made around the early 2000s, getting good at this thing called virtualization, which is to say, making it look like to your code, there is nobody else running on the system, when in fact there are. And your virtual machine will stay on that processor, on that rack, for as long as it's turned on. Now, the moment you turn it off, it doesn't exist anymore. Your files are stored somewhere, but there is no actual CPU that's being given the work that you are told is important. The next time you turn it on, it could end up anywhere else. And so now there's this question of, what does it look like when a lot of people are creating virtual machines? Do we have enough capacity to satisfy demand? Amazon and Google and Microsoft put a lot of effort into provisioning these things so that they can always meet CPU demand. For GPUs, especially because of the global chip shortage, they've had trouble with that. And so we begin getting these notions like resource queues and GPU rations, and it begins feeling like World War II era London. There is an interesting model of virtual machine management called spot instances or preemptible instances, where you say, I am willing to run on whatever machine you give me, and if there's too much demand at any given time, I may get kicked off. And I'll get 2 minutes of warning ahead of time. So I can run a script on my computer automatically that saves my work and gets things ready to turn off. You can think of it as sort of like if there's a lightning storm blowing through your town and you need to turn your computer off and unplug it from the wall immediately, which I always had to do growing up. It's the equivalent of that. And they'll publish rough eviction rates of how often that's going to happen and how likely it is to happen. But the savings cost can be huge. It can be an order of magnitude. And what you're basically saying there is, my computation's not earth-shatteringly important. Which is a weird way to frame this, because what is earth-shatteringly important is being able to go on Facebook.com whenever you want. That's what they view as important, because that's where the money is coming in from. Facebook will pay a lot of money to make sure that their VMs are always available, always there if I happen to go to Facebook.com. But if you're willing to have your work be pausable, and you have to do some engineering work to let it be pausable, then you can squeeze in wherever they have room and possibly get kicked off before your job is done. Maybe if you're doing machine learning and you have different training epochs, then you get to checkpoint at one of them and bring it back later. This is a really good way to save money if you're resource constrained. It's also a lot of work to get right if you want to not impact your own life that much by doing these things. But that's the only place that external the external rate that these things are occupied at really affects what it looks like to you. In terms of environmental impact, this is a really good question, and I don't know that much about how to measure the environmental impact of what running one of these virtual machines is. Other than, I think I have 2 thoughts here. One is, it's huge, and if you look at how much energy goes into just saying doing a Google search, which is effectively talking to a server in one of these racks, which is managed on the Elastic Cloud, which then looks at a database, which is on another rack, and then returns back to you. It's the number of cups of coffee that you can create by boiling water with the energy taken by one Google search is shockingly large. So that's concerning. On the other hand, a lot of these data centers, if you look at where they're physically built, are built in places where there is a lot of naturally available energy. So they'll very often be built, say, in the middle of gigantic plains in Texas, where there is a lot of wind power, or somewhere where it's very easy to cool them, say very far north in Minnesota. And you don't have to pay for a lot of air conditioning, at least not for large parts of the year. And there are even whole startups dedicated to creating data centers specifically in places where there is a lot of sort of renewable earth provided energy for running these sorts of systems. Now, as for whether those are what you're getting when you go onto Azure or AWS, you have some control over what data center you're placing your machines in. But in terms of the environmental impact that has, I think that's generally harder to measure, which isn't to say it shouldn't be measurable. It's just not what they've been focusing on right now. We can change that.
No, just to
Yeah.
correct that, for example, in AWS, you can get, they have a dashboard that tells you exactly how much CO2 your compute has produced.
They do?
They do.
That's amazing. That's really cool.
Okay, just repeat what I said, because maybe the folks on.
Yeah. So Ariel points out that actually the things that I was saying were not necessarily true today, at least on some of the cloud platforms. AWS has a dashboard that can tell you exactly what the carbon impact of your specific virtual machines are having on the data center and on the planet. If I had an AWS demo, I could pull that up.
I'll post a picture of mine.
Oh, good. Thank you. And thank you for correcting that. I didn't realize that they had put that effort in. That's cool. Thanks for the question. It's a really good question. Yeah. Yeah.
Can I ask a theoretical question?
Yes.
So you're saying that the most, whatever you can buy is not realistic for a lot of people, like it's just not something
Yeah.
that is common? So like, what would examples of that be? Like, what kind of company or person would need that much space?
That's a really good question. High performance compute. These are the types of things that really intensive simulations usually take up. So like the kinds of particle physics that they do a lot of work on at CERN. And this isn't to say that all of the work they do at CERN needs these sorts of high performance instances, but like the kinds of things that need to be doing a lot of computation, they're going to be generating a lot of stuff that they need to store, and they need to remember a whole lot of state all at once. And so these are really designed for the places where formerly you would have had a supercomputer that's literally called a supercomputer. And like you would have one in a room and it has like a marketing name and it looks like this. You know, like previously you would purchase these things and maybe you're a geothermal energy company, or maybe you're CERN and you have a lot of funding. Then you put a lot of resources into this thing, and this thing can run simulations of the size that you have data for, whereas nothing else quite will. But that's a really good question. There are also a lot of applications that are just not very well optimized, which isn't to say that they shouldn't be run. It's just that they're going to be expensive to run until people figure out how to, and this is the key to being a good cloud consumer, figure out how to separate the work that you're doing into the CPU heavy portion, and that creates artifacts that go into a memory heavy portion. And later you do some machine learning on that stuff. So you need a GPU instance for this, but you don't need all of them at once. And that takes work to figure out how to separate those things. And work takes time. And our time is worth a lot, and that might not be time that we want to spend. And I work with a bunch of scientists that end up using these like super powerful machines just because they're not computer scientists, they're not going to figure all this crap out, and they have the money to do it. And it's like, it's fine. I just moved across states, and the amount of resources that I blew doing that was pretty disappointing in terms of the amount of cardboard and bubble wrap that I wasted, but it's because I didn't have the time or energy to figure out how to sort them properly. My partner actually sorted a lot of our bubble wrap out and found places that would take it online, and I appreciated that a lot. But I was doing the equivalent of using the high performance compute VMs, you know. Yeah.
Can you give an example in like the kinds of knows these people at this workshop would do, of like a way that someone's refactored code to like split out the compute optimized versus the memory optimized parts?
I could imagine things. I don't know if Ariel might be able to speak to that more effectively.
Yeah, I mean, I'll show later on that it's in some sense, when you're doing massive compute, you're actually better off using a layer of the cloud compute where you don't need to even make those decisions, where those would be automatically done for you. So, for example, I use AWS a lot, so that's kind of my example. AWS has services where you say, I want to do all this computation. Could you just find machines that will do it for me? And then it does. They have tools that do that kind of calculation.
Do you know what that service is called? Like what their brand name is for that?
Yeah, it's called the AWS Batch.
Okay, cool.
Yeah, and I'll talk about it a little bit later
Yeah,
today also.
Just so like make sure that I'm getting it, it's less of like, I need to go through my scripts and reach back to them to be like, okay, like. Image manipulation, matrix stuff is still here, and then like giant averages is still here.
Oh, I see, that kind of thing.
Yeah,
That would be really, really hard to do, right? Look at different parts of the code and say, here I need a machine with lots of memory, and here I need a machine with extra fast CPUs. I don't know that anyone does.
cool.
Yeah.
So we don't.
Oh, no.
I think, yeah, that would be
I mean,
very hard.
I think that this is in practice, like the dimensions that you have to play with. The failure mode for not playing with any of these things is effectively just that things are slower or cost more money, maybe not an astronomical amount of time or money. But they are affordances that you now have by working on this system. So exactly the kinds of things that you were just saying, like doing image manipulation and stuff, and like multiplying matrices together, maybe that is a large part of what you do. But you also have some part of your work that involves just collating all the data sets and figuring out which data you want to actually process. You don't necessarily need to do that latter part on the kind of beefy machine that can do all of the image processing. You could find a much smaller instance to do that kind of thing and then send it to AWS Batch, which will allocate, which manages a cluster. That is one of those cluster management services that creates beefy computers to do your work, gives you back the results, and then deletes those computers so that you're not paying for them after you're done. But yeah, getting concrete about this stuff is always useful. So thanks for bringing that up. Yeah.
So going off of that, would it be more efficient and cost effective and time effective to just hire someone to do that optimization?
Do that optimization in the sense of like splitting things off into like an image manipulation part and a smaller part.
Yeah.
Yeah. Yeah, I think so. And I mean, I think that this is why cloud solutions architect is an increasingly common job title that you see. At the University of Washington, we have this new I don't know if it's an institute. It's not an institute. Well, we have a new organization dedicated to having people called research software engineers, whose job is to think about things like this and also other problems like writing code to do things like this, and pair them with research groups. So actually figuring out the utilitarian like cost to benefit analysis of whether this thing is worth it versus hiring someone to do this versus not bothering with this, I think some people really like figuring that kind of stuff out. I've always been a very fuzzy qualitative person. So I've never been good at doing those sorts of analyses, but I know groups that have landed on all of the different types of answers to that question. They have had grad students that have just decided to really drill down into this stuff and learn it. They've had people that they've hired as consultants to come in and do work for them. They've avoided doing this stuff in general and just bought a computer and it worked fine for them. I think that in general, with computational work that you do, there is a really interesting trade-off curve for how much time you spend trying to figure it out versus what it's actually getting you. And I like thinking about this stuff sort of with a time dimension in addition to an immediate work dimension, thinking, is this going to be useful to me in the future? And my patience for figuring out cloud stuff is very high, as long as I think this is going to be a generalized skill, or this is helping my cognitive abilities to problem solve and understand an inconsistent environment that I don't understand that well. Versus the moment it stops feeling like that, then I rapidly stop being willing to figure out how to make this stuff work. And that's where I'm very glad that like I'm around people who have done things before that I can ask questions of. So there's a really interesting balance you have to figure out for things like this. If you like playing with computers, then it's possible to frame this stuff in a way that it's fun and potentially good to put on a resume. And there's value in that. If you don't like playing with computers, then find someone who is a good mentor and can help you set up the things that you need. And don't bother putting that much time into it. And use things like Colab, which are built to allow you to not think about things like this. But this is a really interesting question to think about. This is actually like what I like dedicated like a third of this slide deck to, is like exactly this kind of question about like when this stuff becomes worth thinking about and how to think about it once you do. But I'm happy to have this stuff show up organically too in conversation. Any other questions? Yeah.
Follow up on that, like. We have, like, at my institution, we also have like some of these resources, and I've always found it a little difficult to like, how do I even propose the question I need to ask the IT person?
Yeah. Yeah.
Part of it is like, you have a folder script, and you're like, I don't even know how much CPU it takes to run this thing.
Yeah.
How does one sort of go about like even asking for, I need this many resources?
Yeah. Yeah. So the question is just in general, how do you figure out what questions to ask of your IT personnel? And how do you figure out like how many resources you need to solve a problem that you have? So I think that in general, the thing that we want to do, so splitting that into how do you know what questions to ask and how do you estimate how much stuff you need. You want to find someone who's not even necessarily an IT person, but someone who speaks your language and has walked the path that you've walked. Maybe you're the first person to do that at your institution, then the challenge is finding those people online or at a place like this, and networking enough with people who seem to have done things using GPUs, and they mentioned they've done it in the cloud. Talking to them about how they've done these things. Because through socializing with them, that's how you begin to pick up the types of schema that you use in your head to think about these things and the way that you ask these questions. And maybe there are people at your IT department whose job is to help with that. So if you see someone with the name specialist in their name, that's like a key sign that they are there to help solve specific problems, rather than be an IT architect or like a systems administrator in the background. So like a lot of the work that me and my manager do here is find the people who want to ask these questions of what questions do I ask? And we get to know their science, and we help them formulate those questions. And then we bring those questions to the people who have the resources, whether that's on-premises computing or whether that's the right program at one of these cloud vendors to get credits to do their work. So I think that like finding your community of practice in your specific subfield that has done cloud computational work, or even you can start with just general computational work, and cloud is just one way to get the numbers crunched. You start following them around and you listen to the questions they ask. in terms of figuring out how much GPU power you need to do a given task, I was just talking with someone this morning about this. It can be really, really hard to know ahead of time unless you've been doing this stuff for like a long time. Like I'm not good at estimating this kind of stuff. And this is where finding micro grants and microgrant slush fund, kicking the tires fund, getting someone to give you like $500 to just do whatever you want on the cloud, and then trying a workload out and just observing and doing this process before you go through any sort of formal request for an actual account that would actually have money attached to it. At the University of Washington, there's, I don't remember what it stands for, but there's the RCC, which is the Student Computing Research Computing Club. And they provide students with cloud starter funds that they can use to try things out. There are a lot of things like this in various places. And so that's another good thing to figure out through networking, which this is also a part of that. This is networking. Figure out where you can get your kicking the tires money.
And Naomi, I just posted in Slack the relevant pages for Google, AWS, Azure, and even Oracle.
The dreaded
all of
Oracle.
all of whom have
Free
will give you
money.
free credits. Some of them will actually ask for your credit card number for you to be
Mhm.
able to use that, but you know, you can close your account after using this.
Mhm. And so you get that free money and you try doing things. And one of the meta skills that you're working on here is identifying how many resources you're using. That's not something that by default we're going to know how to look for or be good at. And so the thing about learning this cloud stuff is it ends up being a whole lot of system administrator IT meta skills that are really, really useful to have just as a general way of project management and working with computers. But it is a big lift. And I remember one of you on Slack posted, like, when I asked what the cloud was, so one of you said, like, it's a lot of preparation work to jump into it. And it's like, it's true, but it's worth it. It's good elbow grease, maybe. But yeah, there's no real way to get good at this stuff without just trying it. And asking people for help. Cool. So let's see. I was talking about VM sizing. Now I want to talk about storage. Let's see, just want to see a little bit of what I'm doing here. Storage, workflows, cost benefit analysis, meta learning, getting our hands dirty. All right, I do want to talk about storage, and then we can look at what the time is and how much of it we have and what we want to focus on. So we just talked a lot about VM sizing. Now I want to talk a little bit about ways that you store files outside of virtual machines. So the first way that you store files is maybe the most common to our daily experience. It's called block storage. And the idea is it's like the laptop hard drive that's plugged into your computer. Or maybe it's an external hard drive that you can swap around to other people. But it's really the closest analogy to how normal computer files work. And this means that it's actually the most expensive because the cloud provider can't do any secret optimization in the background to store things more cheaply for you. So that's why we usually see the capacities for block storage are pretty small by large data terms. They're in the gigabytes range. Sometimes they can go up to a terabyte. That gets extraordinarily expensive. Usually we don't even think about block storage when we're working with cloud stuff. These are created automatically when we create a virtual machine. They're deleted automatically when we delete the virtual machine. And we don't have too much flexibility with regards to how large they are. The next thing that you're going to see in cloud world are standard file stores. And these have different brand names on each of the cloud providers. Microsoft has, or Azure has, I think they're just called file stores. Amazon is EFS, Elastic File Share, EC, is it EF? Has some brand name. And so the idea here is this is sort of like a network drive. Like at your institution, if you have network space that you get as a part of just having your username and password, and you can access it through your computer, it still looks like a folder with a bunch of files in it. You can do whatever you want with it. This is sort of the next tier up from block storage. So you can create file stores. You can share them between virtual machines. You can share them between multiple users. And they're good for holding a lot of data, even potentially like up to 100 terabytes of data. And this is the kind of thing that, if you need to store more than 100 terabytes of data, you can just create multiple file shares. That's okay. This limitation really mostly comes from the fact that your operating system is not used to dealing with that much data all at once. And in terms of price, this is like an order of magnitude less than block storage. So the idea is you keep your long-term files in a file store, or in the next thing we're going to look at. The only stuff that you keep in block storage is what you're actually thinking about and working on in this moment. So you stage the stuff that you actually care about from your data set into block storage, crunch the numbers, and then you delete it. Or if we're talking about file storage, you might not even need to do that. It might just be connected to a folder, or connected and look like a folder in the computer, and you don't have to think about where that file is at all. The important part is that you've gone through this manual creation process of saying, I'm creating this little corral that I'm going to keep all my data in. And while we're talking about little corrals to keep data in, this is where the first real completely cloud native concept shows up that doesn't have an analog for normal computing. And this is called object storage. And so I was struggling to figure out a visual metaphor for this, because block storage is like a hard drive in your computer. File storage is like a bunch of disks in a closet somewhere. Object storage tries to abstract all of this hard drive metaphor away entirely. So when we're talking about object storage, what we're talking about is there's some bucket that you can upload files into and you can download files from. It's not necessarily going to be through a web browser. You can mount these things so that they look sort of like folders, and Ariel is going to be showing you that in just a little bit. And this is a really useful way to work with data sets so that your Python scripts and whatever can look at files the same way that they're used to looking at files. But behind the scenes, this stuff is being stored in a really weird and opaque way. And the cloud provider is monitoring how often you use a given file. And if you use a file a lot, it's kept in hot object storage. And if you don't touch a file a lot, it ends up in cold object storage. And the prices for these vary a lot. And the line between these two is getting blurred a lot these days, which is good. They're making object storage look more and more like file storage, which is to say they're getting a lot smarter about taking files and storing them efficiently in a way you don't have to think about, so that you don't have to pay as much for them. And this is one of the really exciting things that's been changing a lot recently. If we talk about even 5 years ago, there was in practice a huge difference between using object storage and file storage. This is getting less and less over time. And so if we're talking about price, object storage, of course, it varies a lot based on how much you use a given file, how much it costs to store. But fundamentally, we're still looking at a large cost savings from normal file storage. I was actually looking at EC2, or not EC2, AWS's pricing for file stores versus object stores last night. And they were not as big of a gap as they used to be. File stores are getting cheaper. But it's still cheaper than treating things like a normal folder on your computer. And so this is, I think, what a lot of us will be interacting with when we use public data sets that are posted in the cloud, because this is the most cost-effective and scalable way to store huge amounts of data. This is what AWS really pioneered with their open data set registry. Forget the specific name for that, but AWS makes a lot of public data sets available through object storage in their cloud. And that includes all of the data sets in the Open Neuro project. which are accessed. This is actually a screenshot from openneuro.org, and these files are all served from Amazon's object storage, which is called an S3 bucket. Yeah.
Are there any differences when it comes to, I guess, data privacy and security, when you use block storage?
That's a great question. So like, we're talking about, are there differences between data privacy and security when you leave block storage, go into file or object storage? I think the difference between these is not as big as the difference between cloud platforms and sort of whether you're within the specific administrative corrals that they create for privacy compliant data. So in general, all of this stuff is encrypted when you're not using it. In practice, if we're talking about HIPAA compliance or something like FedRAMP that like deals with like privacy sensitive health data, all of the resources, including the network that connects them, or because this is the cloud, the VNet that connects all of these things, needs to be compliant with all of these federal regulations for privacy, which are pretty cool to like make sure that like stuff doesn't get leaked. And all of the cloud vendors have teams that specifically think about this stuff. Some of the cloud vendors publish more publicly available case studies about how they did it than others do. And this is the kind of thing that still takes a little bit of work. So at the School of Medicine, we have set up a few HIPAA compliant case study research programs using the cloud. And ultimately, I mean, it was extremely doable. It took a lot of conversing with the cloud platform to make sure it was all above board in the right way. Do you have any experience with working with privacy sensitive data on these storage media?
Yes, I do.
Do you think there are any considerations when we're talking about object versus file versus block storage for that? Or is it a higher level?
No, all of them you can enforce encryption, which is important for preserving privacy. And you need, if you're dealing with kind of data, you need to make sure that the default is for the encryption not to be turned on. You need to make sure that the encryption is turned on at all the levels that are possible here, and then you're working now within the virtual private network and all those things. So it's a bit beyond the default is the thing that's tricky here. You go beyond the default setting.
Yeah, but it's a really good thing to suss out that you're asking here. Like, if you have to think about that when it comes to choosing which of these things you're using, it's less about one of these things can and the other can't, and more you have to just remember to pay attention to this with everything you do on the cloud. And that's why you have these things like secure computing enclaves. The idea is that every single piece of it has been created with this thought to when this data is encrypted and who holds the keys to that encryption. In general, things can be kept very securely on the cloud, possibly more securely than in on-premise computing, because the data centers are managed by someone who has a vested interest in that security. Like the security faults are usually from the user's side, like from the way we set things up, rather than a fault at Amazon or at Google. But these are really good things to think about.
Then 15 minutes left.
Okay, yeah.
I was gonna say, so I'm a practicing therapist and we're not allowed to keep anything on our personal computers, it all has to be in the cloud.
Yeah,
You have to find it in that box.
that's really interesting to hear, because like,
I use like a remote desktop and everything, I can't keep anything online.
yeah, from the perspective of like tech support, like helping people set things up, it's always like, oh, I don't know if I'm going to be able to make the cloud secure to do my work. But then the thing is, once it is secure, it is probably more secure than most solutions you'll find elsewhere. So thanks for the lived experience perspective there. Yeah. So when we talk about storage in the cloud, we're thinking about these three different types of storage. In practice, most of the data sets we'll use are going to be in object storage, whether we've created those data sets or whether we're using ones that others have uploaded for us. And what that's going to look like when we're doing our work is that we'll start with a full data set that's in object storage. We'll download the files that we're interested in. We'll stage them into a folder in our virtual machine or on our laptop. We'll run our Python scripts, do the things we want, get our outputs from that. And then we'll upload the results back to object storage and delete everything in our staging folder. So the idea here is that the staging folder is in block storage. It's in the hard drive on our computer. And we're only using this to do the work that we need to at any given moment. We're not keeping the whole data set there. And as soon as we're done with things, we sort of wipe them. We keep our cooktop clean. And whether you're doing this on your literal laptop or on a virtual machine, when you're working with object storage, this tends to be what the workflow looks like, unless you're using something that manages the object storage so that it looks like a folder full of files. And this is getting increasingly common. So we're increasingly not having to worry about staging things versus not. But it's still a useful metaphor to think about in terms of efficient places to keep data versus the place where your computation is actually happening. What are you moving around and when? And this is the kind of thing that, again, like if you make a mistake here and you don't delete things as soon as you're done with them, nothing bad happens, but you might find that your hard drive fills up. And then you have to clear your hard drive out. And eventually you go, ah, I'm not deleting these files after I download them from S3. That's okay, I'll delete them now at the end of the script. And there you go, solve the problem. So that's all that I have for abstractions. I have some slides that describe what workflows look like. I'm gonna just breeze through these kind of quickly because as a pedagogist, I'm interested in meta skills about learning rather than things themselves, but please, if you're interested in or want to talk about any of these more, then we can slow down. But what we just talked about is sort of a data warehouse model where you keep all of your stuff in object storage, all of your data sets in object storage. You do your computation on your local cluster or your laptop. The problem with this is that it can sort of be like throwing money away if you're managing the object storage yourself. And that's because of this specific problem that some people really encounter and others, depending on their institution, don't have to worry about, which is to say, in general, getting data out of the cloud costs about 10 cents a gigabyte. Just to say it's metered that when you download a file onto your computer from object storage, it'll cost about 10 cents if it's a gigabyte large. This isn't true across the board because universities tend to work out contracts with cloud vendors such that this fee gets waived. You can also, if you make your data set publicly available and open, or if it's not your data set that's publicly available and open, then this fee gets waived. And that's where AWS's open data sponsorship program becomes really, really helpful. The other vendors have similar programs, but they're a little bit less scaled out and fleshed out. But in general, this is sort of a financial bottleneck for using the cloud this way. And that's why people are increasingly putting their computation in the cloud itself. So the idea is we have our object storage with our full data set. We create a virtual machine to do that Python stuff. Because even though we could do it on our laptop, doing it all within the cloud is effectively free because we don't, or it's the data transfer between these two is free because we don't have to download it all the way to our laptop. And the way that we do this is by installing Jupyter Hub, which lets us run this code on this computer using a web browser on our laptop. And this is the model that we see increasingly in large data set management. This happens with the Dandy archive for neuroimaging. This happens with Pangeo for geoscientists who are working with a lot of seismic data and stuff. They have large clusters of computers running Jupyter Hub so that they can log in with Chrome and run Python code on the data set that's in the cloud already. And this saves a lot of money because even though they have to rent the virtual machine, if they have a lot of different scientists all doing this at once, they don't have to download this data 300 times to everyone's laptop. And so the last workflow that I think we see commonly is this notion of having clusters, and this is serviced by things that Ariel mentioned, like Amazon's AWS Batch service, which gives you a computer that you can work on sort of with Jupyter Hub the way you're used to interactively, but you can also submit jobs to run on clusters of CPUs that scale dynamically so that you don't need a whole lot of them before the deadlines for publishing, but maybe you want to get things done the night before. So you submit a bunch of jobs, CPU cluster scales up, does the work, scales back down. And this has been sort of facilitated by new technologies like Nextflow, which is a programming language specifically for describing pipelines of data processing that are split into different stages. The Sherbrooke Connectivity Imaging Lab has a bunch of examples of Nextflow scripts for doing neuroimaging available on GitHub. That's definitely worth checking out. And so then I have some slides talking about when the cost is worth it. And these are the kinds of analyses that really depend on your specific project. But if we talk about the price for storing something in the cloud versus on an external hard drive, it on paper is cheaper per gigabyte to store things on an external hard drive. But this doesn't give you things like redundancy and like automatic backups that you get in the cloud. And if you're going to make copies of that data set and share them with your colleagues, then you can think about this cost as sort of being amortized by just keeping it in the cloud and letting everyone work on the same copy of something. Similarly, if we talk about doing a lot of intensive computing and we get a really powerful computer with a bunch of GPUs, then that's going to have some upfront cost, and we'll be able to use it over a period of like 5 years or whatever. Or we could rent that machine for an hourly rate on Amazon and pay about $1.74 per hour for it. And we can even reduce that cost by saying, I don't always need GPUs. I need GPUs for this machine learning step. So when I'm doing machine learning training, I'm going to rent the $1.74 per hour thing. But when I'm just doing sort of normal number crunching and stuff with NumPy and things, I'm going to use a compute optimized instance, which is cheaper than the big beefy GPU instance. And when I have to do a bunch of data set sorting and management, then I can go for a memory optimized instance, and this saves me even more money. So I think that the cloud can look very expensive. The way that it becomes worth it is by treating these things heterogeneously, saying that these resources can be really sized to fit your needs. And if you take the time to figure out how to size them, then you can make things work well for you. So I have another prompt, and I was interested in what the obstacles were, and we were going to brainstorm that. But I like the discussion that we had better. I just wanted to show you this GIF of a dog who's. Yes.
So do those GPU instances allow SSH access?
Yes, they do. The GPU instances do allow SSH access. And in general, almost all of the compute things that you interact with on the cloud allow you to SSH into things.
Does that include Google Colab?
It does not include Google Colab. And that is an example of where the platform as a service becomes a little bit stifling if you want that level of control. So I think that, I don't know, do you know if Google Colab lets you open terminals to like?
I believe so, yeah.
Okay, so you can like.
So far I know Google Colab requires Jupyter Notebook server to access.
Yes, though it automatically has that. So yes, so you access it by logging into their notebook interface. And you can open a terminal to run things like pip or conda, but ultimately this is all avail on top of a computing environment that is very packaged up and abstracted away from you. The idea is for you, if you're using Colab, to not be thinking about things at the level of using a terminal. And it's there if you absolutely need to think about it. but you wouldn't be able to say SSH into that without using their web terminal interface. And so if you want to start thinking about using these things as machines that you don't log into interactively, that's where we begin to use sort of these cloud virtual machines rather than the consumer platforms that we're discussing as convenience features. So like we were talking about AWS Batch as a way to conveniently submit jobs and like have the code run and then have the machine be deleted as soon as you're done. You do not have SSH access to the machine running your code on AWS Batch. You have insight into what's going on. You have the logs, you have like control over what type of machine is being created. And of course, you provide the scripts that actually run code, but you cannot log into it interactively. And these are the trade-offs that you start facing when you look at things like this. Well, I want to give Ariel time to show you guys some cool demos, but I've uploaded the link to this slide deck to the GitHub repo for NeuroHackademy 2022 under Alterman-Cloud. And so I encourage you to send me emails with questions if you have any. I'm going to create a slide with my email address on it so that you can get in touch. But I'm around and I want to hear from you. All right.
And we're basically out of time. So I could follow up with other things on, or we have a review sessions tomorrow afternoon or breakout sessions sometime next week to look at some more of this stuff. But I can do, actually, we'll see how our data showcase goes tomorrow. I can kind of run some things. You'll see some like cloud accessible data sets at tomorrow's data showcase, and we can look in more detail at our code, pulling parts of the data.
Oh, I'm so sorry.
No, no
It's
worries.
spaced out
Yeah,
about what times things were ending. Well, yeah, thank you all for the spectacular discussion. These were all really good questions. And like, I think the way to be thinking about this stuff as you begin engaging with it. So yeah, there are plenty of people here that know how to do this stuff. I sort of know how to do this stuff. So as you network and get to know people, learn to answer or learn to ask the right questions and be in touch. We're all here to help you.
Thanks, Simon.
Yeah.
And goodbye, Zoom people. We'll see you all tomorrow morning.
Goodbye, Zoom people.
Ariel, city question, how are you?